is Dr. Sirisha, working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to discuss about the linear data structure known as queues and its implementation using linked list. Let's have a look at what a queue is and what are its basic operations. So a queue is a linear data structure which is having a provision of inserting and deleting the data at two different ends. Means insertion is possible at the rear end, whereas deletion is possible at the front end. These two operations are named as enqueue and dequeue respectively. That is, enqueue is adding an element, whereas dequeue is removing an element. So in queues, this is the restriction which they have given. The linear queues, the first and foremost one, linear queues. First in, first out. That is, the element which first enters the queue is going to be removed first. Okay, so enqueue is adding, whereas dequeue is deletion. These are the only two elements on which we have the access rights. Say if your queue is something like this, which is having elements. Okay, have a look. 1, 2, 3. That means your front is pointing to 1 and your rear is pointing to 3. Right? If you want to insert an element, insert at the rear end. So if I want to insert 4 at the rear end. If I want to remove an element, that is dequeue, I'm going to just increment the front. Now my front is pointing to 2. The intermediate elements, except the elements pointed by front and rear, do not have any access. We do not have access rights to the intermediate elements. That is the beauty of linear queues, right? So privilege of working with only the end elements, the front and back elements, is the only provision we have. These are the two primary operations that we can perform on a queue. The remaining operations are to check whether the queue is full or not, to check whether the queue is empty or not, what is the element pointed by the front, and what is the element pointed by the rear, are the 4 operations that we can have when we work with queues. First one, what is easeful? Easeful is a function which works on overflow condition. Then what do you mean by overflow condition? That is the first point. Easeful money, it is going to check for overflow. Okay, then what is this condition? If the size of the queue is n and you have inserted n elements into it, and if you are trying to insert n plus 1th element, then there is no space for that. In such cases, easeful function returns true, saying that an overflow condition has reached. You cannot further insert an element into the queue. Okay. The next operation is empty. It is a function which is going to work on underflow condition. Then what is this underflow condition? Underflow condition is a condition which tells you that if the queue is empty and if you want to remove an element, if you want to perform dequeue operation on the queue, then how can you remove an element from a queue which is already empty? Then we can say that underflow condition has reached, and thereby isEmpty function is true. It says that the queue is empty. These are the two conditions which the functions useful and isEmpty are going to use. And these two functions are used for enqueue and dequeue operations respectively. Right? Next, front. Front is the function which is going to display, or it is going to retrieve the element pointed by the front, and rear is a function which is used to retrieve the element which is pointed by the rear pointer. Okay, these are the overall 6 functions that we have, or we have and we can perform on queues. Let's have a look at them one by one. Okay, let's have a small comparison between stacks and queues. Have a look at this one. If the elements are A, B, C, D, E, right? Then the top element in a stack is going to point to the most recently inserted element, which is E, right? If the same set of elements are inserted in your queue, then first insert A, front and rear are going to point to A. Then you insert B, front will be there only, whereas rear is going to increment itself. Then you enter C, front will be as it is, as this is an NQ operation, only rear is going to increment itself. At the last, when you insert E, your front will be as it is, because all the operations were NQ operations only. We didn't perform any DQ, right? So the front will be as it is, whereas rear is pointing to the last or the most recently inserted element E. So this will be the structure if you try to insert or store data using stacks and queues. Okay, in this order, A, B, C, D, E order. Okay, so have a look at the queue operations or queue using linked list. Let's implement queues using linked list. Okay, so the node, basically the class function is used to create a node, right? Whenever an object of class node is created, say new node is equal to node of the name of the class followed by any data value, say 20 is given, then a new node will be created with its data part as 20 and its next part as none. This is nothing but your new node, right? So this init is the constructor of the class node in Python. With the bits and pieces of Python code, I'm going to explain you guys. Okay, so this is how it is. And the new node next part is none, because initially when a node is created, it is not linked to any other element in the total structure of a queue, right? This is the first element of its kind. So its next part is none until unless you build a relation of it with the remaining elements of your queue. Okay, so this will be the construction of a basic node in a queue. The next second class will be QLL, which required represents queues using linked list. Okay, and its constructor is having two parts, front and rear. Okay, so front and rear both are initialized to none. These are the two variables which are, or I can say these were pointer variables, which are going to hold the addresses of the nodes. Rear is going to hold the address of the most recently inserted one, and front is going to hold the address of the one which was entered first, right? So these are the two pointer variables which the constructor of QLL is going to use. Let's look at the operations ENQUEUE and DEQUEUE operations. Okay, ENQUEUE operation, that is insert operation, right? So I'm going to read the data first of all, which I have to insert. Then I'm going to create a node by calling the object, by creating an object of class node, thereby calling the constructor of the class node. Thereby it is going to create a node. It is going to create a node with a data part and the second part as none. As I already said, it's at the initial stage, its address part will be none. That is, the next part will be none. Now let's perform insertion operation. It has two cases, case number 1 and case number 2. What case 1 tells us about? What do you mean? How can you insert an element into a stack if its front is none? Or you can also state, what if its self dot rare is equal to none. Guys, recollect, when will the front and rear are going to hold none? Case where the queue is empty, right? There is no element in the queue itself. The node which you have created just now is the first node of its kind. When the case is something like that, then we have to think the node which you have created as it is the first node, then to that node, which one is going to point, front or rear? Both are going to point the same node. Means whatever the new node which you have created, say if it is at location 2000, then rear is going to hold 2000, whereas even front is also going to hold 2000, specifying that the only element that is present in the linked list is the new data, the new node, right? This is the case where you have just started creating a queue. What if already queue is existing, that is queue is having handful of elements, now you have to insert the data, right? That is the else part, right? Now you have to store, where you have to insert at the rear end, right? So rear next, the next, that is the address part of the next, will hold the address of the new node, whereas now it is the job of the rear to increment itself or to point to the new node. So new node's address will be stored in the rear, right? So now rear is pointing to the new node. So these are the two cases where we can perform enqueue operation of any queue. Okay, let's have a look at the animation of the same. Have a look at this one. So have a case one where a node is there. This is nothing but your node whose address is 4000, as this is the only node that is present in your queue. Front as well as rear, both are pointing or holding the address of the first node, which is 4000, right? This is case 1. Please make a note of these animations, my guys, because including addresses, I have gone with the explanation of the operations of the queue. Okay, case 2. Have a look at this one. Here, handful of elements are there. 21 and 22 are the elements. Start, as usual, start is holding the address 2000, which is a pointer variable which holds the address of the first node, right? Guys, have a look at this one. If we represent the same using queues, how it is going to look like, right? 21, 22. 21 is at a location 2000 and 22 is at location 3000. This is 21 is the front and 22 is the rear. If we implement the same, if we want to see, have a look at the structure of the same in terms of arrays, this is the structure. Okay, there you do not need the start, because as the data is linear in fashion, if you know the address of the front, job done. You can get the addresses of the remaining. Okay, so this is the case, and now you have to insert an element. Where you are going to insert an element in terms of a linear queue? At the rear end, right? Something like this. Let's have a look how it will be done. Have a look at this one, right? So whatever the new node that is being created is going to be like this. Okay, so its address 4000 is placed in rear's next part. What is the rear holding? 3000. 3000's next part is over here, which was previously now. It is going to hold 4000 now, which is the address of the node which I am inserting now, and I am going to increment or update the content in the rear, saying that now your rear is supposed to hold the address of the new node, which is 4000. This is how I am going to insert an element in a queue. Let's look at DQ operation, that is delete operation. To delete, I have three conditions. Just like the three conditions which we have seen, the deletion, that is proper operation of a stack. Similarly, we have three situations or conditions to perform DQ operations on a queue. Okay, the first one tells us about a case where the front is none, or even you can write if self rear is equal to none. This is the case where we are going to know that the queue is empty, elements are not present in the queue itself. How we are going to delete or remove an element from an empty bag, right? So from an empty queue, how can you perform this task? So you simply say return or print empty and return. Or even you can say that the queue is full, sorry, empty, the queue is empty and return, right? This is the first case. And the second case, have a keen look at the second case, guys. What if front and rear are pointing to the same element? Okay, and I would like to add one more condition here, saying that and self dot front is not equal to none. This will be more clear for you guys. What do you mean by these two conditions? First of all, let's go with the second condition, which says self front is not equal to none. What does it mean? It means that the queue is not empty, it is having few elements. If it was empty, then front would be holding the value none. If it is not holding the value none, means that it is having elements. And condition is that even rear is pointing to front. Both are pointing to the same element. What do you mean by this? It means that there is only one element present in the queue. Guys, try to imagine if single element 21 is present in the queue. Obviously, front and rear are going to point to the same element, as well as front is not equal to none also, because it is pointing to 21, which is at location say 2000. Front will be holding 2000, right? It is not none. As well as even rear is also pointing to the same element, that is holding the same address 2000, right? It means that only one element left in the queue and we have to remove it. What will happen if you remove the only element present in your queue? If we remove the only element present in a queue, the front and rear are going to backtrack or come back to their original default values, which is none. Okay, these are the two cases. Coming to the last case, a case where the queue is neither empty nor having a single element. It is having handful of elements. A case where it is having handful of elements. Then you have to remove an element which is pointed by the front. Very good. So let's give a dummy name temp to the element pointed by the front. Okay, then front next, whatever the front and next is the address present in the next, I'm going to assign it to the front. That means I am taking a hop, taking front, make a hop, making front to make a hop, and thereby delete the temporary. That is it, delete the front. Okay, these are the steps. I'll show you the else part, that is a third case with an animation. Please try to understand and follow it as I have depicted this pictorially using addresses. Okay, let's have a look. This is case 1, right? A case where only one element is present in your queue and your rear and front. Have a look at this one, guys. Both are holding same value and both are not equal to none also. Obviously, they are showing 4000, right? Then what we can do, just make them as none and tell that if you want to give if you want to throw a user friendly statement, you can throw saying that the queue is empty now if you have removed the last element present in the queue. Okay, yeah. The next case, have a look at this picture, guys. If we take it in terms of arrays, if I try to redraw this one using arrays, then 21, 22 and 23 are the elements I have, which is they are located at 2000, 3000 and 4000 locations, and the element front is pointing to the element 21, whereas rear is pointing to the element 23. If you want to insert an element, you can insert any element after 23, and if you want to delete an element, you have to delete the element at 21 and make your front hop and point to 22. And I'm concentrated in deletion operation right now. So I want to remove the element present at location 2000, which is element number 21. Great. Let's do that. Simply by making the front address, that is the self dot front dot next, which is 3000, into your start. Override the content 2000 with 3000. If I do that, have a look at the change which I have done. 3000. That means now the start is pointing to the node which is present at location 3000. And now self front, whatever the front is, right? It is going to hold the address which is pointed by this. It means if you write it in sentence form, self dot front next, whatever the content is present in it, place it in start, right? Then next is in self dot front position. Okay, in its sorry. Let me write in the reverse order. I think yes. Self front, whatever the content in start is there, because start is going to hold the address pointed by the front, right? So copy it. Now thereby you can see that you have deleted the contact or the content which is present at location 2000. It is not holding any data now. Now the front is being moved to the next node which is 22. Start is holding the address of the node 22. Everything is changed. Now if you just use the operation del temp, which I have named it as temporary, just remove it, job done. Deletion of the element present at the front and is done. Okay, so this is a delete operation. Remember guys, DQ operation has three cases. Case 1, a case where the queue is empty, that is underflow condition raised. Next one is a case where the front and rear are pointing to the same element, that is they are pointing to the only element that is left in the queue. So once you remove that element, you have to bring front and rear to its default values, which is none. Okay. The third case is a case where the queue is having handful of elements. So what you have to do, you have to just make the next element of the front address stored in the start, so that start is going to point to the second element, and make the second element as the new front element and delete the old front element. Okay, so this is as a whole the pop operations that you can have. The three cases under pop operations which we have in a queue. I hope I'm clear with it. Now have a look at the traverse function. What do you mean by traverse? That means a case where we are going to hop from front element to the rear element, because that is the list of the element that we have in our hands, right? So let's have. So even here, even when I am trying to display, or how can the system or a person knows that it has the code which you have written hops from one node to the other. If you print the content in the node, when you take each hop, then you can say that yes, the function is working well and it is hopping proper, right? For that purpose, I have named it as display function. Okay, and as usual, I'm going to take the precautionary step which says that if front is equal to none, that means if front is holding the value none, then the queue is empty. As I already said, even you can use the condition self dot rear is equal to none. Guys, remember, if front is none, then by default rear will also be none, and vice versa. There is no change in that. Okay, if one is in none, the other will definitely be none. There is no change in it. Whatever queue you take, circular queue, double-ended queue, any queue you take, the basic fundamentals of a linear queue must prevail. It will not going to change. Okay, yeah. Come back to our display function. First case is over. The second case where there are elements in the queue which we have to print. From where we are going to start that? We're going to start from the front and to the rear. We all know that there will not be any gap between the in the cells. In the cells, from between front and rear. If you want to delete, you are going to delete from the front. If you are going to insert, you are going to insert at the rear end. There is no point in thinking that you will have empty spaces between front and rear pointers. There will never be empty spaces. So I'm going to start my printing, that is traversal from front to the rear. Why front, ma'am? Can't we have the default value as 0? Just have a look at this point, ma'am. I'm taken an array with the indexes 0 to 5. Okay, basically this is an empty one. Front and rear are pointing to none. I've inserted a value 21. My front and rear are pointing to both. Right? Then I have inserted 22. What will happen? Front will be as it is, whereas rear is going to point to 22. Right? Now I insert 23. What will happen? Front will be as it is, whereas rear is going to point to 23. Now I insert 24. Then my rear is going to get incremented and pointing to 24. Now I perform DQ operation. I try to remove the element which is present in the front. I have removed the element at the front end. Now my front is pointing to 22. Okay. Now I'll do one more DQ operation. I'll remove 22 also. Now my front is pointing to 23. Now have a look at this current. Now I want the current status of the queue display. So what do you think? If I print from index value 0 to 5, am I going to get the exact queue? Or from front to rear, if I print, which one will give me the exact current status of the queue? Obviously from front to rear. It is not mandate in queues that front should always be at 0 or the rear should always be pointing to the highest or something like that. No, it is not the case. We can never say that front is pointing to 0 index value always. And coming to the linked list representation, there is no point of talking of indexes also. Do we have the concept of index? No, right? So from front to rear, I'm going to use my printing. Okay. So have a look at my code. So I've taken a dummy name temporary. I've given front that name, and while my temp is not none, it means if you implement the same using linked list, okay. So if it is at location 2000, this is front 23, it will be holding the next node's address 3000. Say 3000, this is a rear 24, this is none, right? So until unless my temp is none, right? I'm going to print the content button and I'm going to take a hop, right? This is nothing but your traverse function in your queues. Okay, so guys, please do remember it is not in case of stacks by default the starting point is 0 or the first one is 0, but here we don't have that. We have to start from the red and end at start at different and end at the red. Okay, this is the traverse function. Let's look at the advantages of linear queues. The basic advantage is it can hold multiple data types and flexible, and it can be extended to any length. Okay, this is the basic advantage which we encountered in case of what you say when compared to your stacks, right? I am not comparing stacks with queues, but arrays, you can say arrays and linked list versus. So arrays have predefined fixed length limits, whereas linked list do not have. Even though linked lists suffer the space complexity problem, because as you extend the size of the nodes, that is the number of the nodes in your queue, the amount of memory which is required to store the next element's address also increases, right? Which increases the space complexity of the queue. But it is worthy enough when we look at the advantages and applications of linear queues. Okay, basic disadvantage of linear queue. Why it is not beneficial at times. When we implement a linear queue using arrays, what is the condition which tells you that the queue is full? If your array is pointing to the last element, last indexed value. Okay, if the array is pointing to the last indexed value, that is array is equal to max size minus 1, then we say that the queue is full. Okay, the queue is full. Right. So even if, as I've shown in the previous example, even if the 3 cells here are empty, but we cannot use them to insert. We cannot use them to insert. Simply because the array is pointing to the highest index value, we simply say that the queue is full and further insertion cannot be possible. Overflow condition raises. So that is a basic disadvantage of linear queues, which we are going to overcome when we go for circular queues. Circular queues solve the major problem of the linear queues, that is utilization. If you pictorially look into this one, the fifth one, so if you can link a list, 1 is linked to 2, 2 is linked to 3, 3 to, and 4 is linked to the 0th element. With this linkage, we can say that the disadvantage of linear queues we are going to overcome. Even using linked list, we can overcome this tragic thing, that is we cannot saying that we cannot extend because you have reached the maximum index, because linked list do not have linked index values concept, and so it does not suffer this problem which arises when we implement linear queues using arrays. Okay, right. Coming to the applications of queues. Okay, so queues are used for resource sharing. That is, when multiple consumers are there, just like in the purpose of CPU schedule and disk scheduling, to a single resource is there. Suppose your disk is there, which has a huge content, then multiple sources can extract data from it, right? It's not that you can give read-only permission to all these 5 users, right? This is a disk. Clients, 5 clients are there. You can give read-only operation to these 5 clients so that they can read. No need, as they don't have the right to write on it or manipulate it. So only read operation. Everybody can read it. Multiple users, right? So resource sharing is one of the big applications, huge applications of your queues. Next important application is when the transfer is asynchronous in nature. I'll explain you what it is. For example, here is a source and here is the destination. Packets of data you are sending from source to the destination. Very good. The source is very fast, it is sending its packets very fast. Whereas your destination is very slow, it is not able to receive them so quickly, right? So, what happens is that the destination is going to maintain a queue. So, whatever the packets that come from the source, it is going to place them in queue. So, first come, first serve. So, whatever the packet that is going to first come, it is going to take it. So, I can say that the link changes something like this from source to the queue of the destination, queue of the destination. Okay. So, it is going to store the data. It is going to use queue as an intermediate storage device, and it is going to store the data, and it is going to retrieve it one by one, right? So this is an asynchronous way of transfer, as a case where the source and destination are not at the same place, right? And that is the rate of data sent by the source is higher one compared to the rate of data the destination receives or the receiver receives. Okay, so at that time the destination uses a buffer, which is nothing but a queue. Okay, then the next application of queues is semaphores. First come first serve scheduling, whatever the scheduling technique you take, memory management, scheduling of operations. First come first serve is the basic, right? So spooling in printers, buffer for devices like keyboard, right? So all in all these things, queues will be immensely used. Coming out of the simple computer, when it comes to networks, so queues in routers and switches and mail queues. Mail queues, you might know that, right? It's a familiar one. And queues in routers. Routers use store the data and transmit. They energize it, reboot it, and send it. Right? If the signal becomes weak, right? They boost it, amplify it, and they do not change it. Please remember that they do not change the content, they just amplify it and retransmit the data. And to do this process, they must store the incoming data. For that purpose, also, they are going to use queues. Okay, I hope, guys, I'm very clear with the queues and basic operations on queues. Then the advantages, disadvantages, and applications of queues, right? In my next video, we are going to talk about and discuss about the basic applications of stacks and queues. Stacks and queues are two different types of linear data structures, as you all know. There is no comparison between these two. Stack provides the access to the data from only one end, which is either push or pop from the front end only, the only one end. The other end is sealed, which we cannot. Whereas queues provide the access in both the directions, but it suffers with a few drawbacks, as you cannot access the data which is at the front end. It is a bit difficult one. So they have come up with circular queues and double-ended queues. Circular queues is a queue where the last element is linked to the first element. That is, the last node is going to hold the address of the first node. Thereby, we can run in a circular fashion, right? So that will be easy to work with. And double-ended queues. A double-ended queue is a queue which is having special privilege, where front and rear ends are going to get the privilege of implementing both the operations. Say, generally rear end is meant to perform insert operation. There in double-ended queues, you will get the privilege of removing the element at the rear end also. Okay. Coming to the front end, normally front end is meant to remove an element, right? In double-ended queues, you will get the privilege of inserting an element at the front end also. Okay, and these double-ended queues you can implement using in a linear fashion or in a circular fashion also. Generally, they are enhanced versions of step by step. If you say linear queues, circular queues, and double-ended queues are implemented using circular queues. Okay, so these are the three which we are going to discuss in my further sessions. Hope I am very clear with the things which I have taught till now, right? So catch you with the remaining videos in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.